to perhaps this will be the last lecture in the series of lectures on color science and management. So in the previous lecture I had talked about a whole lot of different issues regarding how to standardize print processes and all of that. In this lecture we would be talking about two things that I have left out from the previous lecture. So remember this particular schematic on the implementation of color management. I had left out two issues. One was the gamut mapping part and the other was the black printer generation. So as you know, first I will start with this followed by this part. Okay, so as you know that the CMY printers, I mean the CMY subtractive primaries are not sufficient enough in order to reproduce an image with printed image having high fidelity with the original. Why is that? Primarily because of the fact that they have hue deficiencies, inherent hue deficiencies, which make them deficient in order to produce the required colorimetric specifications as is wanted from them. So in order to prevent that from happening, or in order to essentially improve the quality of print, or bring this equivalency of color appearance between the print and the original, we need a fourth printer, which is known as the black printer. That has to be, so the black printer has to be added to the CMY printer in order to produce the final CMYK print. Now there are several techniques of adding or generation really, or optimization of this black to the CMY images. So I will be talking about two such methods in this particular lecture. So the first method I will be talking about is known as UCR, or this is referred to as undercolor removal. Now why undercolor removal is, you know that black is, for a 4-color sheet fed offset press, black is the first down ink. So the printing ink sequence is first black, then cyan, then magenta, then yellow. This is a standard printing sequence which is laid down in various specifications, as in ISO 12647/2, and this is something you will see in all the most of the presses across the world. Take any standard printer in the market today across the globe, and 95 to 97% of them would be using this sequence, and people who don't use this sequence, you do not use this for particular reasons. But the standard printing sequence is black being the first down color, second down color is cyan, then magenta, then yellow. This is a standard across the globe for sheet fed offset press. Now in undercolor removal, UCR stands for undercolor removal. In this process, what is actually done is, the black being the first down color, it is considered to be the undercolor. So we remove black to what degree, or we are saying we remove black, but essentially what we are doing is we are replacing. So the terminology may be confusing, but try to understand, or try to, I think, take a look at this particular picture. So this is your CMY image. So this is your final CMY image. Now this image is inherently deficient in hue and inherently deficient in the details. It lacks certain shadow details. So in order to add those details, what we do is we add some amount of black in the shadow. This addition of black, take a look at which areas black is replaced. Take a look at this, which area the black is replaced. Black is replaced in shadow areas, specifically in shadow areas, and along the neutral axis. What is the neutral axis? Areas in the image where cyan, magenta and yellow superimpose on each other. Only specifically in these neutral areas black is replaced. CMY is replaced with black. So this is one way of optimizing the ink, black ink or black addition. Now take a look at this particular image. This is basically the color representation, all the color how they are arranged in this particular image. So take a look at this. This is the neutral axis, right? Now I am adding black in which part of the image? I am replacing CMY, that is chromatic black and replacing it with achromatic black in which area? The shadow area of the image, as well as in the neutral, somewhere along the neutral axis of the image. So this is the CMY image, this is the black image. So together, when they will be printed in sequence, we will get the ultimate CMYK image. Now this type of black modification is sometimes referred to as narrow and long. Why? This black is replaced only narrowly in the neutral axis of the entire image, along the neutral axis of the entire image. Areas where saturation is low, that means CMY together, they superimpose. And why narrow? Because narrow and long, I mean, they are black is being replaced, achromatic black replaces the chromatic black in shadow areas and in a very narrow stretch of region which encompasses the the neutral gray axis of the image. That is why this type of black optimization is known as undercolor removal, and also by the other name, which is narrow and long black, right? In addition to this, there is another type of black addition or black removal, black modification, which is known as GCR or gray component replacement. If UCR is considered to be narrow and long, black is considered to be wide. Now take a look at in which areas chromatic black, which is in, I have already given you the idea regarding chromatic and achromatic black. So chromatic black is obtained by the combination of C, M and Y inks, and achromatic black is only black ink. So in which areas black is replacing the chromatic black? In almost all areas of the image, specifically definitely in the shadow region, but almost in all areas. See, the replacement of achromatic black replacement of chromatic black by achromatic black is taking place almost throughout the entire image. Just just observe this particular image, only the black channel of this particular image and the black channel of this image. See, where is the black replaced? Where am I replacing the achromatic black with chromatic black? In primarily in the shadow areas. See, these are the shadow areas, right? These are the shadow areas. So I am replacing chromatic black with achromatic black only perhaps in the shadow areas, right? But in case of GCR, where I am replacing the chromatic black with achromatic black almost throughout the image, except for the highlight area, almost throughout the image, in shadow, definitely in shadow, and also in a large quantity of the mid-tone area. That is why, since the region of replacing chromatic black with achromatic black is almost throughout the image, that is why this is referred to as wide black replacement. Okay, so together this is chromatic black and this is the CMY superimposition. This is achromatic black and this is CMY superimposition. Together they will form the ultimate image. Now you will not be able to fully understand and appreciate this unless I tell you the reason for doing so. See, chromatic inks, that is cyan, magenta inks, are very costly in nature. Okay, so if your ultimate aim is to produce black where C, M and Y superimpose or juxtapose together, not superimpose but juxtapose, then it is it makes sense to replace the chromatic black with achromatic black, which is cheaper. The second point is, you consider any area. Okay, so any area where there is C, M and Y, 3 dots and 3 inks falling on top of each other, so there might be several problems owing to this, because there might be a possibility of increased dot gain, of increased tack in those areas. Then there will be piling and all these issues will occur. In order to avoid that, if you can reduce what is known as the total area coverage, TAC, total area coverage, how much amount of total ink is being used in a maximum amount of ink that is being used in a particular area. So in sheet fed offset process, standard TAC is maintained at 240%. মানে দেখো, যদি CMY 4টি ইউজ হতো তাহলে টোটাল এরিয়া কভারেজ would have been 400% maximum, that is 100% of cyan, 100% of magenta, etc. But for there would have been so many problems. কি পরিমাণ ডট গেইন হতো, কি পরিমাণ সেট অফ হতো 400% TAC করলে। তো it is being capped at 240% TAC. Now the advantage, as I already mentioned, why you do this UCR, why do this GCR. So firstly, in order, that is to reduce the cost of the ink that might be required and optimize the ink, and also to improve the quality. How improve the quality? By reducing the dot gain, by reducing the set of problems, all this. So that is why UCR GCR is done. তো এটা তো গেল থিওরিটিক্যাল ব্যাকগ্রাউন্ডটা। এবার এটা একটা মানে হাতে কলমে না করালে জিনিসটা বোঝা যাবে না। সেটা হচ্ছে, দিস ইজ ইয়োর let us say this is your original image, and we will be doing some UCR GCR operation on this image. So let us see what will be the effect of UCR GCR in this particular image. So what you have to do is you have to select custom and CMYK also here custom, and just take a look at it. In this case, two options are there for black generation. One is GCR, this one, and another is UCR. Now আমি পরপর দুটো জিনিস দেখাচ্ছি। হ্যাঁ, এখানে দেখো টোটাল ইঙ্ক লিমিট, এটাকেই আমি বলছি টোটাল এরিয়া কভারেজ। এটা 300 করা আছে, এটাকে আমি 240 সেট করব। ঠিক আছে, তাহলে যদি 300 হতো, সরি 240, হ্যাঁ, yes, so this is set at 240. Now what I will do is I will show you two things. First I will give I will use heavy GCR. Heavy GCR করলে কি হবে, this is the highlight area of the image, this is the midtone, this is the shadow area. তাহলে when I am using heavy GCR, তাহলে how much black is being added, in which region, শুধুমাত্র আমি আগেই বলেছি যে GCR is basically wide black addition throughout the image. শ্যাডোতে তো বটেই, হাইলাইটে অতটা হবে না, কিন্তু মিডটোন শ্যাডোতে ভীষণভাবে ব্ল্যাক, হাই অ্যামাউন্ট অফ ব্ল্যাক এডিশন হবে। তাহলে here you see in highlight region, is there any black addition? No, there is no black addition. Black additionটা কোথা থেকে শুরু হচ্ছে? হাইলাইটের পর থেকে মিডটোনে প্লাস shadow region a huge amount of black addition হচ্ছে. This is what is known as heavy GCR. Now in contrast, if I give you the example of light GCR, see in case of, just compare, take a screenshot and compare. Since I am replacing chromatic ink with achromatic ink, that is chromatic ink meaning cyan, magenta, yellow, I am replacing with black ink, the amount of chromatic ink has reduced and the amount of achromatic ink has increased. Now in case this is heavy GCR, where addition of black is huge, high. Now if you use, instead of heavy GCR, light GCR, that means black will be added but not so much. So here you see almost till midtone area there is no black addition. After midtone area there is huge amount of black addition. Automatically, since the amount of achromatic black has reduced in this up to midtone, from highlight to midtone area, automatically in those areas chromatic inks has increased, quantity of chromatic ink has increased. Just compare here, see here black addition starts almost right after highlight area. ঠিক আছে, সেখানে chromatic ink গুলো কমে গেছে, achromatic ink টা বেড়ে গেছে throughout. But in case of light GCR, what is happening, chromatic ink has increased and black addition has decreased till from highlight to midtone, midtone এর পর থেকে আবার black addition টা হচ্ছে। ঠিক আছে, so these are the various types. Depending upon your requirement, you will add black to your image using GCR. Now come to UCR. UCR এরকম লাইট হেভি ব্যাপারটা কনসেপ্টটা নেই। UCR এ ব্ল্যাক এডিশনের যে ব্যাপারটা সেটা এমনিতেই কম হবে, দেখতেই পেয়েছো, কারণ UCR আমি বলেইছি ইট উইল বি ন্যারো অ্যান্ড লং ব্ল্যাক, মানে মোটামুটি ধরে রাখতে পারো শ্যাডোতেই বেশিরভাগ ব্ল্যাক এডিশন হচ্ছে অ্যান্ড অ্যালং দ্য নিউট্রাল অ্যাক্সিস ব্ল্যাক এডিশনটা হচ্ছে। তাহলে লেট আস সি, তাহলে এটা যদি হেভি GCR হয়, যেখানে ভারী মাত্রায় ব্ল্যাক এডিশন হচ্ছে রাইট আফটার দ্য হাইলাইট এরিয়া, ইউসিআরটা কীরকম কী হচ্ছে দেখো। ইউসিআর কিন্তু টিল অনেকটা লাইট GCR এর মতো ইউসিআরটা স্পেসিফিক। তাহলে ইউসিআরকে আমি অনেক সময় বলি, আই রেফার যে ইউসিআর ইজ এ স্পেশাল কেস অফ GCR। ইট ইজ ট্রু। ইউসিআরে কী হচ্ছে, ইউসিআরে কিন্তু দেখছো ফ্রম হাইলাইট টু মিড টোন দের ইজ নো ব্ল্যাক এডিশন, অনলি ইন বেসিক্যালি ইন দ্য শ্যাডো এরিয়া অ্যান্ড সাম অ্যামাউন্ট ইন দ্য মিড টোন এরিয়া। তাহলে এখানে দেখো the amount of chromatic ink has increased till mid-tone area, and achromatic ink, there is no achromatic black over here till mid-tone area. After mid-tone area till shadow, black is there, and amount of chromatic ink has reduced. So this is basically your narrow and long black addition, and GCR is your wide black addition. বুঝতে পারছো তো? একটা স্ক্রিনশট নিয়ে দেখতে পারো যে এটা একটা স্ক্রিনশট নাও আর এটা একটা স্ক্রিনশট দিয়ে দেখো যে এফেক্টটা কি হয়। এটা ডু দিস টাস্ক অ্যাট ইউর হোম and tell me what observations you made in the final output of an image. You do this thing and tell me what changes you will observe in the quality of the final image. Okay, just let me know. Okay, so this is one thing. Right? Yes, and next, before going to the next thing, what I need to do is really okay, now one thing that I have left out is the gamut part and the rendering intent, that is gamut mapping part. Okay, so what is a gamut? Gamut is সেরকম মানে হাইফাই কিছু না. Gamut is what? এটা তোমাদের, this is your xy chromaticity diagram. তো তাহলে for any process, gamut refers to the total number of colors that a particular imaging process can reproduce. So for, as you know, a display monitor will reproduce larger number of colors than your printing process, offset printing process. You agree or disagree? Agree, obviously. So the reasons is known to you, the reasons are known to you now. So obviously maybe a Apple computer monitor will have larger will be able to reproduce larger number of colors than your mobile device, right? So like this. So gamut is what? Gamut in English, gamut is basically the perimeter, the perimeter that a particular thing occupies. So here, as you take an example of this, is the gamut for Adobe RGB. Adobe RGB is a device dependent color space. The gamut is this triangle, right? This particular triangle, big triangle. But this one, this purple colored, this gamut, this is basically the gamut of your swap CMYK, that is standard wave offset printing CMYK color space gamut. So number of colors that may be reproduced using your this standard wave offset printing technique is much less than what can be reproduced using a display monitor. So this is what gamut is. Now the problem is, you see, this is your input gamut, this is your source gamut, right, or source profile or source color space, whatever you say it, and this is your destination gamut, or destination profile, or destination color space. Now invariably what happens is the printer's gamut is smaller than the input and the display's gamut. So there are colors which are present in this region in case of the display for that particular, what happened, yeah, there are colors that may be present in this particular area in the digital display which may not be reproduced in your print. So what to do, what technique to follow? There are several techniques by which you can actually bring out of gamut colors, so colors which are lying maybe here inside this gamut. This technique is, but this field of study is known as gamut mapping. So it's a very basic way I will try to explain. So here is this another tool. You can see a good visualization. So your the outer gamut, this is the mesh type of structure. You see, this mesh type of structure is your outer gamut, which is your sRGB gamut, which is a display or input color gamut, right, or input color profile. Whereas this inside inner gamut, the inner gamut that you have, this inner gamut is representing the printer's gamut, which is in our case, which is the Fogra coated Fogra 39, the characterization, the profile or color space based on that particular characterization data. So which is larger, which is smaller? Of course, the inner gamut, which is the Fogra coated, that is the printer's gamut, is smaller, whereas the input gamut, that is the monitor's gamut, is much larger in size. So this is basically your another visualizing tool. So let me explain how you can reproduce out of gamut colors in while printing. Basically there are several techniques to do this. These are basically known as gamut mapping. The first type of method is known as perceptual rendering intent. In perceptual rendering intent, what happens? So let me just try to draw. So this is, let us assume that this is your input gamut, this is a triangle, and this is your, let us say, output gamut. Okay, so this is your input, this is your output. So your output is smaller than your input gamut. So what happens is, in case of perceptual rendering intent or perceptual gamut mapping, what happens? The out of gamut color, so let us say there is a color which is present over here. The out of gamut colors are mapped to its nearest color. The out of gamut color, which is in the input color space, is mapped to the its closest color on of the output color space or the output gamut. This is your input sRGB, let us say sRGB gamut. This is your quoted for the printing, this is your quoted Fogra gamut, right? So let us say there is a color over here which you want to reproduce, but it will not be reproduced until you do something. So how to reproduce this color? In using the perceptual rendering intent in the color management system, you can map or bring this particular out of gamut color to its closest in gamut color lying on the Fogra coated color space, right? And automatically, so there are colors here also that are within the gamut, they will also be shifted to some other place. So similarly, there may be another color over here which you want to reproduce, which may not be reproducing generally, but in case of when you are using perceptual rendering intent, what happens is the out of gamut colors lying over here are mapped to its closest in gamut color, and automatically the colors that are lying at that point in the within the printer's gamut, they also get shifted to some other point. Proportionally they get shifted. So like this, you go on doing all this for all these colors. So all these colors from out of gamut will be mapped to inside the gamut. So jodi ki map mane ki dhoro eiটার value jodi x1 y1 হয়, ঠিক আছে, আর এটার ভ্যালু এই পয়েন্টের ভ্যালু যদি সাপোজ x2 y2 হয়, তাহলে যখন আমি প্রিন্ট করতে যাব তখন অ্যাজ ইফ x1 y1 টাকে ইকুয়াল করব x2 y2 কে, যেটাই x1 y1 ছিল সেই কালারগুলো এখন হয়ে যাবে x2 y2। সিমিলারলি এই x2 y2 যেই কালারটা ছিল সেইটা আবার এইখানে চলে গেল, তো শিফট হয়ে গেল, তো তাহলে সেইটা আবার x3 y3 হয়ে যাবে, এরকম করে হবে। সো দিস basically gives you a very good output in terms of defining relative differences in color. Mane when you move, if you do this, if you select this type of a rendering intent or gamut mapping technique while printing, you will see there is a very smooth transition between shadow areas to mid-tone areas to highlight areas. This will give that effect. Okay, so this is one type of rendering intent. The second type of rendering intent that I will be talking about is known as the relative rendering intent. Okay, so relative rendering intent কি হয়? Relative rendering intent কি হয়? So here it moves the out of gamut colors to the closest in gamut colors, but the only different same process, মানে ধরো এটা যদি তোমার মানে আউটপুট গ্যামাটটা হয় আর এটা যদি তোমার ইনপুট গ্যামাটটা হয় আর কি, ঠিক আছে, তাহলে আউট অফ গ্যামাট কালার উইল বি ম্যাপ টু ইটস ক্লোজেস্ট ইনসাইড গ্যামাট কালার, বাট প্রবলেম ইজ এইখানে যে কালারগুলো ছিল এই কালারগুলো কিন্তু আর সরবে না। দিস আগেরটায় যেরকম পারসেপচুয়ালি উই হ্যাড সিন দ্যাট ওয়ান্স উই ম্যাপ আউট অফ গ্যামাট কালার্স ইনটু ইনসাইড দ্য মানে টু ইটস ক্লোজেস্ট ইন গ্যামাট কালার, দ্য কালার্স দ্যাট আর নিয়ার দ্যাট inside that gamut will also get relatively shifted, সেটা কিন্তু রিলেটিভ রেন্ডারিং ইন্টেন্টে হবে না। ওকে, এর ফলস্বরূপ যেটা হবে, আমি যেটা বললাম যে পারসেপচুয়াল রেন্ডারিং ইন্টেন্ট there will be very smooth transition between highlight, mid-tone to shadow, সেইটা কিন্তু এখানে রিলেটিভ রেন্ডারিং ইন্টেন্টে হবে না, সেটা অনেকটা চপি এফেক্ট দেবে বেসিক্যালি। আচ্ছা, নেক্সট there is another type of rendering intent or gamut mapping technique which is known as your saturation rendering intent. Saturation rendering intent কি হয় যে the saturation in this saturation of the color, মানে কালারে তো তিনটে প্রপার্টি, that is hue, saturation, lightness. The saturation component of the color is fixed at the cost of hue and lightness. So here if you can imagine the gamut to be a 2D, that is, so here it may be L and this is the hue, so the C, that is the chroma component, that will remain constant. Okay, so you will only be, so suppose this is your in gamut color, mane this is your in gamut output gamut and this is your input gamut. So input gamut, all the colors will be shifted, from the output gamut to the nearest color in the inner gamut or the printer's gamut, provided their saturation or chroma value remains fixed with the variation in only the lightness and hue component. Okay, this is basically your saturation rendering intent. Okay, this is your third type of rendering intent. Now there is another type of rendering intent which we use very much, we as proofers and printers we use very much, which is basically known as the absolute rendering intent. Ki hoy je again here also same thing, you know, so here suppose this is your so let us say this is your, you know, XY chromaticity diagram, and this is, for example, this is your input gamut, this is let us say RGB gamut, and this is let us say your printer's gamut, right? So what happens, this is your absolute rendering intent. This is your absolute rendering intent. So here what happens, all the outside gamut or all the outside colors are brought inside of the gamut by mapping, you see. But what happens is the white point meaning the area of least saturation, where in case of displays where all the lights are, all the pixels are you know, switched on with highest intensity, and in case of paper, in case of printing, there is no ink. That is the white point. That means paper, color of the paper or color of the, when all the pixels, red, green and blue pixels are switched on, that is the white point of the media. It is also known as the media white point. So for your displays, it is where R value is 255, blue value, green value is 255 highest intensity, and blue value is also 255. For paper, for printing, white point is the what? Paper color. ঠিক আছে? So what happens in absolute rendering intent is the media white point is not considered, it is omitted or it is not shifted. What happens, you see, if this is the media white point of your you know, monitor or your digital image, and this is the media white point of your you know, paper, what happens is when all these color outside colors or out of gamut colors are mapped into inside the color, the media point is not shifted. The media point is basically remains the same. So in case of, if we are trying to simulate the output of printed output in a monitor using a image editing software, we will not, although we will map all the out of gamut colors inside the gamut, and we will replace the out of gamut colors to its nearest color lying on the boundary of the printer's gamut, but the paper's white point, that means the paper's XY value or the LAB value of the paper will not be shifted. এর থেকে যে এফেক্ট, এর ফলস্বরূপ কি হচ্ছে বলতো, যখন আমরা ইমেজটা দেখতে পাচ্ছি না, তখন একটা টিন্ট দেখতে পাবো। ধরো পেপারটা ব্লুইশ, হ্যাঁ, পেপারের মধ্যে ওবিএ দেওয়া আছে, তাহলে আমরা যখন এই অ্যাবসলিউট রেন্ডারিং ইন্টেন্ট করে কালার স্পেস কনভার্সন করছি কোনো একটা ইমেজের এবং বলে দিচ্ছি যে উই উইল ইউজ অ্যাবসলিউট রেন্ডারিং ইন্টেন্ট, তখন ইন দ্যাট কেস দ্য পেপারস অরিজিনাল কালার, দ্যাট মিনস আনপ্রিন্টেড পেপারের যে কালারটা, সেইটা কিন্তু আমরা ডিজিটাল ছবিটার মধ্যে দেখতে পাবো। এটা কেন দরকার হয় বলতো, যদি পেপারটা একটু নীলচে হয়, সেই নীলচে একটা টিন্ট চলে আসবে। ইফ দ্য পেপার ইজ yellower, that yellowish tint will appear because we are not shifting the white point of the image of the color gamut. We are keeping the white point fixed, we are keeping the white point constant and changing all other colors. তার মানে সব কালারগুলোর মধ্যে ওই একটা মানে টিন্ট চলে আসবে। আমি সবগুলো কালারকে শিফট করিয়ে দিয়েছি, অল দিস আউট অফ gamut colors are shifted and mapped to inside gamut colors, right? কিন্তু the white point of the media has not been shifted. যদি white point of the media shift করা হতো as in relative rendering intent, তখন the paper's original color would have been lost. তাহলে প্রিন্টিং এর পর if the paper is yellowish in nature, তাহলে একটা warm appearance আসবে। if the paper is bluish in nature, then একটা cool appearance আসবে। সেইটা আমি আমার মানে মনিটরে সিমুলেট করতে পারতাম না। তো এই কারণেই আমরা হার্ড প্রুফিং যখন করি বা সফট প্রুফিং যখন করি, during those time we use absolute rendering intent so that we take into consideration the media white point of the paper on which the digital image is to be printed. ঠিক আছে? তো এইটা হচ্ছে এই কালার গ্যামাট ম্যাপিং এর যে ব্যাপারটা, যেটা ওই করা হয়েছিল আর কি। তাহলে আমাদের যদি স্লাইডটায় আমরা ফিরে যাই একবার, তাহলে এই যে জায়গাটা, তাহলে আলটিমেটলি কয়েকটা জিনিস করা হচ্ছে। আরেকবার একটু এই স্লাইডটা যদি দেখি, তাহলে দেখো, from device dependent color space to XYZ, how is it done? Using your A to B LUT of your input profile. After that rendering intent apply করা হচ্ছে on that particular image, ঠিক? After rendering intent is done, that particular image is converted back to its XYZ or device independent color space using what? B2A transformation of, no, actually CMYK image, CMY image, XYZ থেকে CMY image. This, how is this done? This is done using B2A LUT of your output profile. এটা যদি sRGB profile হয়, এখানে আমি যেই যদি ফগরা প্রিন্টিং কন্ডিশনে প্রিন্ট করি, তাহলে দিস উইল বি ফগরা কোটের যে প্রোফাইলটা আছে সেইখানকার যে B2A LUT আছে সেইটা দিয়ে I will convert again from device independent color space to CMY, and from once I obtain the CMY, I will use ink optimization technique. I will either use UCR or GCR, and ultimately I will get my CMYK image, ensuring that this CMYK image and RGB image has, this CMYK image is basically a manifestation of these embedded or preserved RGB values, which ultimately ensures that between these two images, that is RGB image and CMYK image, there is a equivalence in color appearance or color constancy between both input and output image. Okay, so before we finish, let me just this is a task I am giving you. Like here you see, as you talked about, as we saw the color, how to do color conversion in color management system in this particular image. So what effect it will have, what effect the various rendering intent will have on the ultimate image quality. So here you can see that we are using what? The absolute colorimetric indent. Take, then what will happen if we are using relative colorimetric? Yes, so see, absolute color, in case of absolute colorimetric indent, we are seeing some darkening happening. Why? This has taken into account the white point of the paper that is to be used in this particular reference printing condition using FOGRA 39. It uses a specific type of paper, so considering the media white point of that paper or the substrate, absolute colorimetric intent is showing me the output that I am likely to get. So this is basically a good example for soft proofing images before printing. But in case of relative colorimetric intent, there is no the white point has been shifted, the output white point has been mapped into the input white point, right, along with the out of gamut colors being brought to its closest in gamut colors. So this is not a very good representation of the final image output that I am going to get after printing. So in case of saturation, the saturations in this particular image you won't be able to see very much difference between saturation and perceptual, but let me just show you what the difference is between perceptual. In perceptual, it will give you very close or very good shifts from the light to from shadow areas to midtone and ultimately to highlight areas. Okay, so my question or the assignment that I am giving you after this is for you to find out two scenarios I am giving. You have been tasked with printing the Coca-Cola red logo. What for this particular color, when you are concerned with brand colors, you want to exactly match your digital color, digital Coca-Cola red with the printed output. So in this case, when you are entrusted to reproduce brand colors, okay, logo colors, what type of rendering intent you have to use, and also in case of commercial work, what type of editorial work, what type of rendering intent you have to use. Also, the final part, I wanted to talk a little bit about one important point that is to be added with that has to be studied together with while talking about relative colorimetric intent, is something which is known as the black point compensation. So when you are using relative colorimetric intent, when you are mapping the input white point to the output white point, so similarly you have to also map the white point of the input to that of the output. Now why is it essential? So typically the input color space will have a darker black point than that of the output print. If the black point compensation is not used, the shadow areas could be losing a lot of detail and some amount of, so here as you can see, we have not switched on the black point compensation part, right? So what has essentially happened is, in the shadow area, as you can see, a lot of detail has been lost. So why is this happening? Because the input's black point, that means in order to the ability of the input digital image to digital display to produce crisp pure black is much higher the capability is much higher than that of the printing, because inherently our inks are hue deficient in nature. So in order to overcome this problem, and in order to ensure that the black the shadow areas detail is lost in the shadow area, we switch this black point compensation on. So after switching this on, try to see that the lot of the image detail that was initially lost without using the black point compensation has been obtained back. So with this, I think we come to an end with the in the color management and color science lecture series. So I hope this was useful to you, and from next week onwards we will start the remaining portion. We'll try to complete the remaining portion of digital prepress. So if you have any questions regarding color science, so tomorrow I'll be taking a special lecture. I'll be conducting a special lecture where I will be addressing all the doubts that you have regarding this. Okay, so thank you, and hoping to look forward to hearing from you soon. Okay, thank you.